In this short video, we discuss the concept of sound quality. Sound quality is the ability of humans to detect differences between different instruments, including instruments of the human voice. So if you hear one person speak or sing, you can tell the difference between that person singing and, for instance, your parents singing. Why? In particular, why can you tell if for instance, trumpet plays the C note, and you know it's a trumpet rather than if a clarinet plays a C note? And the answer to that is, anytime you have one of these instruments playing, they don't just play the fundamental frequencies, but they also play their overtones. And those overtones are played with different amounts of intensity. So in fact, any sound that you hear, if we were to plot this, say as some amplitude versus frequency, we would see some primary frequency, and it probably wouldn't just be a single frequency, it would have some small range. Usually people plot these in like a histogram fashion. Not very well drawn, I admit, but something like this. So this is like the fundamental frequency. But then there are also secondary frequencies, the overtones. And they're with different amounts. So one instrument might have this much, and another instrument, for instance, might have a similar amount here to what I've drawn, but it might have more of this and maybe less of this one here. And what you hear is a superposition or summing of all these waves who have different frequencies. Now, a certain frequency has a certain quality that you like or don't like, and when people talk about it, they talk about your sound quality or your tone quality based upon whether you make a sound that's pleasing or what have you. Another musical terms that are used for this are called the timbre, or like I said, tone quality. So if you're in music or band and they say you don't have very good tone quality, it's because you are getting probably other frequencies here that are undesirable, or the ratio of these frequencies is not what is seen as good for your particular instrument, not pleasing to the human ear. When you plot the frequencies like these versus amplitude, there's a name for that. These are known as Fourier transforms, and when they're done by computer, they're usually called fast Fourier transforms because they use a particular special mathematical technique to get these. So this is called a Fourier transform. Logger Pro can do Fourier transforms. If you hook up a microscope to the Logger Pro interface, it can actually acquire any type of sound you want and break it into the fundamental wave frequencies, and you can play with this. Beats. Sometimes you have two instruments or two tuning forks or whatever that are close in frequency, but not quite exactly. Now, what happens is what happens all the time. When you have two waves that are put together, say wave 1 like this, and you have wave 2 that maybe is slightly different. Let's make it a lot different for a moment. Then what happens is you add those two waves together, and if you had them like this, what you would get is a wave that would look like the slower wave with the ripples from the top wave on top of it. And you get kind of a complicated shift. But what happens if the two waves are close together and about the same in amplitude is that you get a wave that follows the basic wave pattern, but whose amplitude can vary. at a slower rate. What that means is that you get the regular wave, but the amplitudes constructively and destructively interfere as the waves go in and out of interference over a long time. And this gives the sound of a rising and lowering pitch, kind of a whoa, 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 whoa type sound. This is known as beats. And the beat frequency can be found, that is, how long it takes between, or how many times I should say, that you hear this large amplitude over a given time is related to the absolute value of the difference in the two frequency. So F1 is much faster, you get a lot of these ripples. F2 is much faster and they're almost the same, but you get this much smaller frequency due to the rising and decreasing amplitudes because of these two going together. Now, let's show you a simple problem. These are not hard to work out. And again, you can create beats and see this in Logger Pro if you play with, for instance, two tuning forks that are close together. A clarinet plays middle C with a frequency of 262 Hertz. The person next to them, because of the way they hold their mouth or their embouchure or the way they fit their reed, will have a slightly different tune. This clarinet produces a tune of a frequency 265 Hertz. If they're close but not quite in tune, you can hear a beating, which can be very annoying. What is that beat frequency? Well, to find that, we simply take 265 Hertz, subtract 262 Hertz, and it will beat at a frequency of 3 Hertz. Now you might note you can get exactly the same beat. You get the same beat frequency. If the clarinet, the second clarinet, wasn't playing 3 Hertz higher, but was playing 3 Hertz lower at 259 Hertz. It's just the difference between the two frequencies. If the frequencies are exactly the same, the frequency of the beat is 0 Hertz, and you don't get the beat. If they're really very, very far apart, then you can get a very fast beat. But what happens is what I said before, you don't tend to get the constructive and destructive interference to create the huge change in amplitude. And because our hearing is not sensitive to changes in amplitude that well, we just don't hear it and it goes away. They sound like two totally different notes. So then they'd just say you played the wrong note. This is one of the things, of course, people in band know, that they have to be careful. Not only do they need to tune their instruments daily, but as they play, they need to listen, because as they move their mouth around, for instance, on the horn, they can change the frequency and move themselves in and out of pitch, making their band not sound very good. All right, that finishes this section of the course.